Welcome to this lecture on network analysis. Before we proceed, I have a little assignment for all of you students. I want you to read section number 5.3, that is the uh, geometrical interpretation of the derivatives. I want you to read this section from the book. It's on page number 123 of the book that we have been following in the class. Once you read this section, after that you should watch this video. So I want you to pause the video and read this section thoroughly and then proceed with watching this video. All right, so after you have watched the video, we'll start with the next portion. So the next topic is basically problem solving. So in the previous few classes, I have discussed some circuits with you, and I have also I have solved some problems with you, and you have, and maybe you would have done some problems on your own as well. So for solving for these initial conditions, you must always know that there is no set procedure, as in no unique procedure, in the sense that if you are given any circuit and you are asked to solve for the circuit variables or the circuit parameters, there is no unique procedure that you have to follow. Okay, so it's just like a game of chess, you know. The way you start your first move, that's going to determine how you will choose your strategy and all. So as we solve some more examples, you will see a pattern emerge, and this pattern is that we usually solve for the initial values of currents and voltages, solve for initial values of currents and voltages, and then proceed to solve for the derivatives. Okay, so how do we achieve this? We start with making an equivalent circuit for any given problem. We make the equivalent circuit at t equal to 0 plus. So if you remember, this t is equal to 0 plus is the circuit just after the switching. Okay, now after you make the equivalent circuit, what you do next, you will solve for the derivatives. That is, you will make the KVL and KCL equations from the circuit, and then these two steps will make the problem into an initial value problem. Okay, what does this initial value problem mean? That you know the circuit condition before switching. The keyword is before switching is known. So you know how the circuit is behaving before the switching action happens, right? Now you are interested in seeing the goal is to see how the circuit behaves after the switching action has taken place. So these are two keywords. One is before, you know, the circuit condition before switching has happened. This is one condition, and the second condition is that you basically want the circuit after the switching action has taken place. Okay, so some basic rules that you must follow, and these rules will hold for all problems that you encounter. We know that we have circuit elements in a circuit elements. Now these circuit elements, they can be capacitors, inductors, and you have the resistors. Now for the resistor does not have any derivative or integral term, so it is the same before and after switching, right? So the resistor will behave same before and after switching. But these two elements, that is the capacitor and the inductor, these have different sort of modes before and after switching, right? So the what we have to determine how what will happen when switching action takes place. Okay, so in any given circuit, if you have capacitors and inductors, you are basically interested in finding out what happens to the capacitors or the inductors after switching action takes place, right? And for the resistors, you must always remember that this is independent of the switching. Okay, so rule number one in this process, replace all inductors with open circuit or with current generator or a current source having value of current flowing at t is equal to 0 plus. So the first rule is, if you have an inductor in a circuit, after switching, rules for equivalent circuit for time t equal to 0 plus. Okay, this is important, this is key. This t is equal to 0 plus. Right after switching, because we have said that current in an inductor does not change, right? So if the current has previously achieved steady state, it behaves as an open circuit, right? We have seen this before. It behaves as a we have said that if there is no current prior flowing in the inductor, then immediately after switching, no current will flow, so this inductor will behave as an open circuit, right? Or if it has some current going through it, then the inductor will be replaced by a current generator or a current source having a value having the value which was flowing before the circuit switched, right? This is rule number one. I'll let me just repeat this rule because I sort of made a mistake while saying this. We know that in an inductor, current, let me write this here, current does not change instantaneously in an inductor. So if no current was flowing in the inductor before switching, so what can we say immediately after switching at t equal to 0 plus? How will we say this? How will we treat this inductor? We will treat this inductor as an open circuit, right? This is point number one. If current is flowing, then at t equal to 0 plus, you replace the inductor with a current source. Okay, this is rule number one. Rule number two, for capacitors, replace all capacitors with short circuits or with voltage sources having with voltage sources if an initial charge is present, right? We have seen this before in the previous examples. Case number one, if capacitor is discharged previously, if the capacitor is discharged or uncharged at t equal to 0 plus, how do we keep the capacitor? We short it or replace it with a short circuit. If capacitor is previously charged, then at t equal to 0 plus, how will we treat this capacitor? We will replace it with a voltage source having a voltage V is equal to Q naught divided by C, which was the charge on the capacitor before the switching, right? This is rule number two for the capacitor. And rule number three for the resistor, resistors are left unchanged. Okay, so in any circuit, wherever you have resistors will always be left unchanged. Okay, now let's take a look at some simple circuits to understand how we proceed in solving circuits. We have already gone through some examples, but this is very important and you must understand this before we proceed. Now, suppose you have a circuit like this. This is your voltage source. This is your switch. This is the capacitor. This is the inductor. This is V plus minus V. This is K switch. This is the capacitor C. This is resistor R1. This is resistor R2. This is inductor L. Now I am interested in finding out the behavior of I1 and I2. Okay. So what this set of rules that we discussed earlier, what does this rule state? That first you must in the question or in the problem, you must read whether they have specified anything about the initial conditions, initial voltage or initial current or whatever. Okay, check. You should always check whether anything has been said on the initial current. Okay, for this circuit, no initial voltage is applied. So you know that this circuit has been unconnected before the switching action takes place. Now at t equal to 0, what happens? You are closing the switch. The switch is closed. Okay. Now what does the rule state? That the moment the switch is closed, you are basically asked to find out the equivalent circuit. And what is the equivalent circuit going to look like? Let me draw it in another color. It is going to look like this. It is going to look like this. The switch K will come here, right? And the rule states that I have to replace this capacitor by a short circuit. Why? Because no initial current or no initial charge was on the capacitor, and I am supposed to replace the resist. I am supposed to keep the resistor as it is, right? This is I1 at time t equal to 0 plus, right? This is the I1 plus 0 plus. This is R1. Now R2 will be also present like this. And what about L? L will be replaced by an open circuit. Why? Because no current was flowing in the circuit before this switching instant, right? I2 0. So you can clearly see that since the inductor behaves as an open circuit, I2 0 plus behaves as what? It is an open circuit, so hence the value is 0, right? So what can we say about I1 0 plus? I1 0 plus is simply the voltage V, which is here, divided by this resistance I1. Now in these problems where you have to deal with initial conditions, you must keep in mind that you have to basically specify this time instant. Okay, this is very, very important. You have to specify the time instant, because if you don't specify the time instant, the examiner or whoever is taking the paper or whoever is evaluating your paper, he will not be able to make out what time instant you are referring to. So remember this, that you have to necessarily mention the time instant about which you are talking. Okay, so now that we have these two values, this is I1 and I2 0 plus. Okay, now what are we supposed to do now? This is one step of the problem, right? This step, this is one part, that we got the initial values, right? Now this capacitor, let me draw a capacitor here with a different color. This capacitor that is present here, which we had replaced by a short circuit, will not always remain a short circuit. Why? Because as the current is flowing in the circuit, the capacitor will start slowly getting charged. It will slowly start getting charged, and there will reach a point where this capacitor will reach its potential, or it will reach the required amount of charge. Similarly, this open circuit will not remain, this I2 will not be always 0. As the current increases, as the current in the circuit, as the capacitor starts to charge, the current will flow in the rest of the circuit. So this I2 0 plus, this term I2 0 plus, is just at the time instant immediately after the switching. So you must not confuse this, that we simply remove the capacitor like this, or we simply remove the inductor, get rid of this. That is not the case. This is just for the sake of simplicity and for the sake of evaluating how these things are going to behave. Okay, so because see, let me draw this once more. The capacitor is present here, right? Same is the case with the inductor is present here, right? So this, because there is no initial voltage, the moment the switch is turned on, this will behave as a short circuit, but slowly capacitor will start getting charged. Okay, similarly this inductor through which no current was flowing initially. After some time, there will be a time when this current will flow through this inductor, right? So it will no longer be an open circuit forever. Okay. Now, when we evaluate these conditions, let me get back to my original configuration. That is this. Now, you have to take a look at this circuit now. This is the circuit which you have to solve, right? You are basically asked to find out the value of I1 and I2 in the circuit, right? So this is the circuit. Okay. Now what should we do after the time after the switching has happened? What is this K now? The K is simply like this. Okay. Now what should be your next step? Your next step should be to simply apply KVL and KCL in this circuit, right? So let's do that. Let's apply KVL in this loop number 1. So it will simply be minus V plus 1 by C integral I1 dt, that is this current, plus R1, this R1 times I1 minus I2 is equal to 0. This is one equation, right? This is equation in loop number 1. And what about loop number 2? We can say that it is R2 times I2 plus L di2 by dt plus R1 I2 minus I1 is equal to 0. This is equation number 2. Where did we get these two equations? We simply got these two equations by applying the KVL in these two loops. Okay. Now you have to basically appreciate that these values, these equations 1 and 2, these are the general equations for the circuit. What does general equation mean? By general equation means that these equations number 1 and 2, they hold for all times. This is very important. They hold for all times, and they also hold for t equal to 0 plus, right? So when an equation holds for all times, the keyword here is all times, it also holds for this particular time, right? What is this particular time? This t equal to 0 plus, this is the time that we have calculated these two values here. We have calculated these two values over here. So using these two equations, we should be able to basically show that these two equations hold, right? So what do we mean by this? Let me write it for you. So I1, so I'll write a statement here. The values I1 and I2 at t equal to 0 plus are known. So what is this value? I2 at t equal to 0 is 0 and I1 is equal to V divided by R1. So these are two known values. Okay, these two values are known to us. Okay, now now see this in this, let me take a look at this equation number 1. If you take a look at this equation, this term is known to us, this term is also known to us. If you see, at t equal to 0, what does the What is the current through the capacitor? Current through, all of the current goes through the capacitor, since capacitor is a short circuit. So this term is also known, right? Similarly, if you see, let me go to the next slide. The term 1 by c integral minus infinity to 0 plus I1 dt is also known, right? Why? Since capacitor is a short circuit, right? Since capacitor is the short circuit, whatever current I1 is present, that current is flowing through the capacitor, and hence this term I1 is that is 1 by c minus infinity to 0 plus I1 dt. This is known to us. Now next, if you go back to the equation here, let's talk about the inductor. This here, if you see the inductor, the term 1 by L minus infinity to 0 plus V dt represents the current through the inductor. Isn't it? This represents the current through the inductor. At time what? At time t equal to 0 plus. Okay. Now, let's go back to our equations. Equation number 2 over here. You see that this term, this equation number 2 has a derivative term. Okay. So what do we do for solving derivatives? We rearrange the terms, rearrange the variables, and if we take this equation, I will take this equation and I'll paste it here, right? And if I rearrange these variables, I will be able to derive this expression, di by dt. This is 1 by 2 r1 I1 minus r1 plus r2 times I2. Okay. This is again the general equation. Okay. Now, if this is the general equation, what can we say about this term dit by dt at time t equal to 0 plus? Isn't this equation like this? R1 times, and what is I1? I1 will be replaced by this term, V divided by R1. Why? Because I1 0 plus we had derived earlier, that was equal to V by R1, correct? And this is minus R1 plus R2 times 0, because I2 was equal to 0. So this di2 by dt at t equal to 0 plus is equal to V divided by L. This is another term that we have found out. Okay. So what is this term? You should not get confused. This is the rate of change of current at time t equal to 0 plus only. Okay, because you have put in specific values. This is, you must take note that this equation will hold only for time t equal to 0 plus. Okay. Now, let me take the first equation that we did earlier, this equation. Let me copy it and let me paste it over here. So this equation does not have any derivative, and we usually don't solve equations with these integrals like this. So what do? We differentiate this. Okay, and what do we get after differentiating this? This v differential of this v will be 0, so this will be simply removed. So it will be 1 by c I1 plus r1 di1 by dt minus r1 di2 by dt equals to 0. So what will I write here? On the left hand side, I'll keep di1, and I'll say that di1 by dt is equal to di2 by dt minus I1 divided by RC. So this is again the, like I said here, this is the general equation. Similarly, this also is the general equation. Okay, and if you see this equation, do we know the particular solutions? We know the particular solution of this at t equal to 0. Yes, we do. We also know this I1 at t equal to 0. So using these two values, these two known values at a particular time instant, that is t equal to 0 plus, we can calculate this di1 by dt at t equal to 0 plus. This is going to be like this. Zero plus. Okay, so using this methodology, what did we basically do? We basically found out the initial conditions of currents, initial conditions of the currents or the voltages, and we also found out the initial conditions of the derivatives of the voltages and currents, of voltages or currents. Okay, now you would ask, why are we interested in finding out these initial conditions of the derivatives? If you take a look at this equation, let me point it out in a different color, this equation, or for that matter, if I point out this equation, these are two derivative equations. If I go on to further differentiate them, if I find out the double derivative of this term, or if I find out the double derivative of this term, what will this give me? This will give me the rate of change of the derivative values as well. So even though from a practical point of view this is not required, but this may come in handy when we are solving these equations mathematically. Because this, if you see this di by dt term, if you see this L di by dt term, we can physically think of this as the voltage, right? We are not concerned with d square, we are not concerned with d square I by dt square physically as such. But from a mathematical point of view, or from a algebraic point of view, these parameters may be required. So you should not be scared to find out. If you are asked to find out how this what this is, di by dt at t equal to 0 plus, or you are asked to find out the double derivative of current, if you are asked to find them out, you should not be afraid. So this will become clear, the need for this will become clear if you go to the assignment, or if you go to the reading that I had asked you, because this term, this di by dt is the slope, right? Di by dt term, this is actually the slope of the curve. okay, and it also determines the curvature of the waveform. Okay, so in the book, you will, if you read the book, you will see that there are a number of cases. Let me draw the different cases for you. This is one particular case, increasing like this. This is another case. This is another case. These are all currents plotted with respect to time. And like this. So the first term is I0 plus is 0 and di by dt at 0 plus is equal to 0. And also d square I by dt square at 0 plus is equal to some constant k which is greater than 0. This curve, this is curve number 1. If you see curve number 2, curve number 2 is for a case where I0 plus is equal to 0, di by dt is equal to k, some constant, and d square I by dt square is again equal to 0. Because this is a straight line, second derivative is, see, this is rate of change of current, it's a constant, so it's a constant graph like this. Second derivative will be 0, right? If you see this curve, the first curve, initial condition is 0, rate of change is initially 0, second is constant, so it is accelerating. This kind of a graph is an accelerating graph, right? If you see, if you relate current to velocity. Okay, now what can you say about this? Initial current is some non-zero value, k greater than 0. What is this? Clearly this is not what can you say about di by dt at 0 plus? This is again 0 here, and the second derivative also by dt square is also equal to 0, because this is again flat, no change, so first derivative is also 0 and second derivative is also 0. And similarly you can find out the expressions for I0 di by dt 0 plus and d square I by dt square 0 plus. You can find them for this curve as well. So with this I'll stop this session, and I hope you have understood the importance of evaluating these initial conditions, and you have understood how to deal with these initial condition based problems. So let me do a quick recap from where we started. We said that we defined certain rules. We said that inductors in an in a circuit are replaced with open circuits or with current generators. Then we said that capacitors are replaced with short circuits or with voltage sources, and resistors are left on their own. Then we said that we are required to find out the initial values of the current just after switching, given by these types of values. That is, you see the circuit immediately after switching and you see how it behaves, and then you find out these particular values. Now after you have found out these values, you go back again to the initial problem, initial circuit, and apply KVL on the circuit, and then find out the circuit equations. And from these circuit equations you find out the currents and voltages. And if required or if asked, you can find the rate of change of current or the double differential of the current, right? So I told you that even though from a physical point of view they may not be that important, but these derivatives are defined. So I gave you 4 examples of curves based on the initial value of the current, the rate of change of current, and the double differential of the current. So in the next video we will solve some problems, and with that we'll come to the end of this section on uh, initial conditions, and after that we will take up another part in where we'll solve higher order differential equations. So thank you, and I'll see you in the next video.